It's now my pleasure to introduce and invite one of my father's last students, I think last but one, Professor Jagannathan, to give this talk on Clifford algebras and L matrix theory. So I just wanted to tell you one thing and not steal his thunder. My father was very proud that he got the idea of the transition from Pauli to Dirac matrices in a dream at 4 a.m. during the 1967 anniversary symposium. And he was so excited by this that the very next day he changed the title of his talk and he spoke about this work. This eventually led to, more than 24 papers in the topic. And one of the persons who was working most closely with my father and who later extended this whole idea to the realm of Clifford algebras was Jagannathan. And he was always very proud that Jagannathan took it into areas in which he was himself not very familiar, such as projective representations of abelian groups and so on. So I think it's very appropriate that Jagannathan is going to talk about this work.
So thanks to Krishna and the organizers of this Professor Aladi Ramakrishnan Centenary Conference, that I have been given this chance to talk on this work. Actually, more than a technical talk, this is my trip down the memory lane, starting from 50 years back. It was 1971 August that I joined the institute. And how I joined the institute is that I was doing my MSc Physics in St. Joseph's College, and I had a friend by name Kuppuswamy in Srirangam, from where I was going to the college. And Professor Ananthakrishnan, N. Ananthakrishnan, who was teacher to Professor Jagannathan and Vasudevan also. He was in Srirangam and he was teaching in National College where my friend Kuppuswamy was studying under him. So Kuppuswamy took me to Professor Ananthakrishnan and introduced me. And we used to meet often because his house was just close by to our house. So he asked me one day where I would like to go, because I told him I want to do research after my MSc. He asked me, do you want to go to Professor Aladi Ramakrishnan or Professor G.N. Ramachandran? He said, Professor G.N. Ramachandran is also his student. And actually in St. Joseph's College, Professor G.N. Ramachandran's record notebook is still kept. And he asked me, he can recommend me to Professor Aladi or to Professor G.N. Ramachandran. So I told him I like theoretical physics. So he said, okay. Then he invited Professor Aladi Ramakrishnan to National College. And he was giving a talk on this generalized Gelman-Nishijima relation. So after the talk, I met Professor Aladi. I told him that I would like to come to math science. So he said, okay, come. So that's how. And before that, even when I had visited Madras, and then in 70 May, June, I had visited math science when I was at the end of my first year MSc, and I had met Professor Jagannathan and Vasudevan. So in 1971 August, after finishing my MSc, I just came here and joined the institute. That's how I joined the institute in 1971 August 3rd, actually. Then at that time, this book, L matrix theory, or this book, L matrix theory or grammar of Dirac matrices, this was in the final stage of proofreading. So the first job I was given was to proofread this book, the final proofreading of this book. Then with proofreading, I got interested in that. And so I started working with Professor Jagannathan on some problems in this. So I will come to that a bit later. But let me now start with what is this L matrix theory or grammar of Dirac matrices. So this book is a collection of some 32 papers, starting with first paper, 1967, that Krishna told you about, that sigma operation, by Professor Alladri Ramakrishnan, Vasudevan, Jagannathan, Santhanam, Sundaram, and P.S. Chandrasekharan. So actually, P.S. Chandrasekharan's thesis was on this, and most of his work is contained in this book. Now let me come to this. What is the sigma operation? So supposing you take a 2 by 2 matrix, which is a sum of these Pauli matrices, then where these Pauli matrices are known, they obey the anti-commutation relation, square is identity, and they also have this relationship. These 4 matrices, identity matrix, sigma 1, sigma 3, sigma 1, sigma 3, they form basis for this Pauli algebra or the Clifford algebra with the 2 generators, supposing I take these 2, and it is isomorphic to the 2 by 2 matrix algebra. That is, any 2 by 2 matrix can be written as is well known, as a linear combination of these 4 matrices. Okay. Now, supposing you take a vector lambda with lambda 1, lambda 2, lambda 3 as the x, y, z coordinates, then L3 square, if you take that matrix and take square of it, it will be lambda 1 square plus lambda 2 square plus lambda 3 square, or the lambda square mod. So L is sort of a square root of this length square, or L is the length matrix. So L, the stands you can take as the length of this vector. Now, this idea can be generalized to some L3 to L5 you take, which is a linear combination of 5 of these. Then Professor Ramakrishnan's sigma operation was take this L3 matrix itself and replace this lambda 1 by L3 itself, which will contain now 3 parameters, and then rename these 2 parameters as lambda 4 and lambda 5. Then if you expand it in terms of lambdas, then these alpha j's, these matrices will be obeying these matrices will be of this type, direct product structure, and they will obey the anti-commutation relation, square will be identity, and these are actually the Dirac matrices. So Dirac did it by taking this, this is well known from his paper, that a direct product and then multiplying them. He got those matrices. Now, these 4, if I take the powers, all possible products of all possible powers, 0, 1, then they form 16 of them are there, and they form the algebra, and it is isomorphic to 4 by 4 matrix algebra in the sense that any 4 by 4 matrix can be written as a linear combination of these 16 matrices. Now, this generalizes. So, Professor Ramakrishnan showed that this process can be generalized to any L to n plus 1. So, supposing you want to go from L to n plus, so we have gone from L3 to L5. Similarly, you can go to L7, L9, and so any L2n plus 1, if you want, then take with L2n plus, you want to go to L2n plus 3, then take L2n plus 1, and this matrix, this parameter, you replace it by L2n plus 1 and rename the other parameters with it. So, as a result, in each step, the matrix dimension increases by 2. Therefore, in L2n plus 1, it will be 2 to the power n dimensional matrix. And this is what Clifford called as 2n plus 1 way geometric algebra. And that is isomorphic to 2 to the power n by 2 to the power n matrix algebra. And this is there in, of course, in those days there was no matrix theory. So abstractly he dealt with this algebra. And in the American Journal of Mathematics, 1878. So this is there in the mathematical papers of Clifford. So it's in our library. What he did actually was that he took the commutation relations of 2n elements and then constructed what he called as commuting quaternions. Actually, what Dirac did was the converse process. He took commuting quaternions, in fact, the sigmas cross I and I cross sigma, these are commuting quaternions, and he constructed his Dirac algebra. Now, another thing Professor Ramakrishna noticed, this is a very nice thing, that supposing you have such an L and L square, you call it some lambda, since it is L square is equal to proportional to identity, the eigenvalues will be plus or minus of some lambda. So, supposing L square is lambda square, then you take L into L plus lambda, then you can see that it is L plus lambda into lambda. Therefore, supposing you call it as U, this matrix, then it will be LU will be U lambda. That means the columns of this matrix L plus lambda are actually the eigenvectors of the L matrix. So this way, he constructed the eigenvectors of the eigenfunctions of the Dirac Hamiltonian in the first paper. And also, one can relate it to free particle Foldy-Matheson transformation, which was done later by Tecumseh and Santhanam. Again, Tecumseh was another student of, before me, he was student of Professor Ramakrishnan. So, now I come to generalized Clifford algebra. See, this anti-commutation relation of -1 can be generalized in one way as supposing Ej Ek is some double omega Ek Ej, where j is less than k and jk is omega to the power n is 1 and omega is e to the power I2 by k. It's a primitive nth root of unity. Then they started working on this, Professor Ramakrishnan, and independently there existed some literature on this by Morinaga, Nono, Morris, Yamasaki, Popoichi, Backhouse, and others. So my thesis was mainly on this, generalized Clifford algebras, generalized Clifford groups, and their physical applications. So basically, supposing you take only 2 of these matrices, then it will be, you can construct the matrices A and B. So this is like that Pauli's sigma 1 matrix is a generalization of that, and this is sigma 3 matrix generalization. If omega is equal to -1, second root of unity, then you stop with this. This will be 1 minus 1, and it will be 1, 1. Otherwise, it's a circulant matrix. And this will obey this. And this A to the power k, B to the power L, they will be forming n square elements, and that will be isomorphic to n by n matrix algebra. That is, any n by n matrix can be written as a linear combination of these n square matrices. So in that, so these are all traceless matrices, And one can get the coefficients of this by simply taking the ck plus 1 by n trace of this. So Professor Ramakrishnan, he expressed this coefficients in a very nice way. He showed that supposing this C is a matrix, that is the matrix of coefficients, and then you form a R matrix, which is, he called it as rearranged matrix. That is, take the diagonal elements and then write down as the first column. Then take the first off diagonal, write down that, and then the corner element you write down as the second column. Like this you form the matrix. Then that matrix R, and S is this Sylvester matrix or finite Fourier transform matrix. Then he showed that C is S inverse R. So the coefficients can be expressed as C is equal to S inverse R. And in fact, in my thesis, I showed how these finite dimensional things can be, from starting with this, how one can get the finite dimensional beginner function and so on. In fact, there is one incident there, that is when I did that, Professor Marshall Stone was visiting here. So I was interested to give a talk in presence of Professor Marshall Stone. So I told Professor Ramakrishnan that I want to give a talk on this in presence of Professor Marshall Stone. So he arranged it for me. And then actually Professor Marshall Stone, he encouraged me very much, and then he gave me some references also where I can look for more things. So in fact, I have thanked him for that in my thesis. So there's a lot of literature on this SC Sylvester matrix, and Sylvester matrix is also the eigenvector matrix for this A. Therefore, S dagger A, S will be the B matrix. And these arise also as projective representations of the abelian group. So, if you generalize still further, supposing Ej, Ek is some Wjk, where the Wjk, it can be any thing. So all this is part of projective representations of abelian groups, and then Professor Ramakrishnan and myself, that was only one joint paper. Otherwise, all my papers were with Jagannathan. So in this paper, we showed how to represent this kind of algebras, starting with these AB matrices. In fact, there is one, that process he called as a product transformation, like product densities. He called it as a product transformation because to represent this matrix, it will be product of some smaller, more fundamental matrices in terms of those AB. It will be a product of powers of those matrices. So he called it as a product transformation. So, and then I have given the full theory of how to represent all these things in the in this. So that paper of ours was published in this. Actually, Professor Ramakrishnan presented it in, I think, in New Zealand, in Rutherford Centenary Conference or something. So that is in this. And the full solution to this supposing you give me any set of this omega jk, then I can give you the matrices that I have in this fourth math science conference, number theory, lecture notes and mathematics edited by Lord Krishna. Now, Jagannathan and myself, we formed actually this group. We called it Generalized Clifford group. That is AKBF, then take these omegas also. Then we found that in the problem of Bloch electrons in a magnetic field, actually the invariance group of the Schrödinger equation is just this group. So we wrote, we did the representation theory of this, and we wrote 2 papers. And here in the second, in that, the representation theory of this, when n is prime or non-prime, when n is prime, it's very simple. When n becomes a non-prime, it's a very complicated thing. That is where I come into contact with Krishna again. Yesterday he was talking about in the banquet, Professor Erdős visit. There I was actually the taking care of Professor Erdős when he visited here. For 2 days, in fact, I was staying with him. I was staying in one room, in another room. Erdős was, so he used to come to the library and we used to be talking a lot. See, he was not sleeping at all. So I asked him, you don't get sleep. He said, I will have a lot of sleep in my grave. He said, and so he, in this second paper, we had to conjecture a number theoretic identity to prove this, but it was only a conjecture. We didn't know the proof of it. So I asked him. So he wrote it down and then did some asymptotic analysis. It is wrong, he said. So it was shocking for me. So then he said, maybe you are right, you ask Krishna. So I gave that thing to Krishna and he proved it. And then he also took that paper in which I had written down in his notebook, in his bag. He went to Sydney. And from there, after a week, I got a letter from a long proof of my identity by Professor Hirschhorn. So that's what made me interested in some number theory, which proved to be later on useful to me. So then from that we went to, I wrote about this, a new form of magnetic Bloch functions and that things. Now I come to another incident about which also Krishna was talking yesterday in the banquet. That is, if you do something, he wants you to write to the top person in that and get his approval. So he was talking about sending his result to Helmut Hasse and Freeman Dyson. So here, there is a paper by Dirac on on a positive energy relativistic wave equation. Not many people know about it. His earlier equation is, so this is in 1971. And there was a student of Professor Santanam who had joined by name H.N.V. Dutt. So, so he and I, so it was actually Santanam who asked me to look at this Dirac's new equation. So I looked at it and then we just, what we did was, we did something that is, let me go back. That is, this equation looks like this. Only difference is now instead of psi 1, psi 2, psi 4 being four independent wave functions, they are derived from a single wave function psi. And this Q1, Q2 are some internal variables which are bosonic variables. So in order to have the solution, these operators have to satisfy, they have to mutually commute with each other, and that leads to the condition. And this equation is, he showed, that has only positive energy solutions are there. And another thing is, this particle, if it exists, it will not interact with any electromagnetic field. So once you put an electromagnetic field, the whole thing goes, there is no solution for it. What we did was we simply changed this I to minus I. And then we showed that that equation will have only negative energy solutions, and everything else what Dirac had done will go through, all the Lorentz representation and everything will go through. And then I told Professor Ramakrishnan, we have done this. Then he said, you cannot tamper with the Dirac's work and then keep quiet. So you have to write to him and get his opinion. So I wrote to him, just in a single aerogram those days, I wrote to him, and from Florida, he was visiting at that time the Florida State University, Tallahassee, in 16 December 1974. He has written, the equation you propose would correctly describe a particle with only negative energy states. It would be the counterpart of the positive energy equation. But of course, it would not have any physical application. That's what yours sincerely, P.A.M. Dirac. So he sent this letter by post. So, of course, this equation, people have tried. Then later, Sudarshan Mukunda tried to change that bosonic variable to parabosonic and so on to see whether it will interact with the electromagnetic field. Then Bracken showed that it won't. The only solution is zero electromagnetic field. It will satisfy. So till now, this equation, there is no application in physics. My own conjecture is maybe that dark matter is this, because it won't interact with electromagnetic field at all. So then let me go to, I will take a few more minutes then. So this AB is equal to omega BA. Entire quantum kinematics is based on this, according to Hermann Weyl, in his book Theory of Groups and Quantum Mechanics. And he derives shows that Schrodinger's representation of P is equal to minus I h cross d by dx and Q is equal to x as a unique one, that is, it has only one inequivalent irreducible representation. This was shown by Weyl and also by von Neumann. And he derived it from this AB is equal to omega BA finite dimensional representation. He says the kinematical structure of a physical system is expressed by an irreducible abelian group of unitary ray rotations in system space. If the group is continuous, this procedure automatically leads to Heisenberg formulation. Our general principle allows for the possibility that the abelian rotation group is entirely discontinuous, or that it may be even a finite group. But the field of discrete groups offers many possibilities which we have not yet been able to realize in nature. Perhaps these holes will be filled by applications to nuclear physics. So first Santanam and Tekamulla, they took the finite dimensional thing, took the logarithm of these matrices A and B, and then they analyzed the commutation relations of those. Later on, Santanam, myself, Vasudevan, we did what we call finite dimensional quantum mechanics of a particle, which is something like a matrix model. And then I even conjectured that at the quark level, this the position will be just a discrete and finite, so that you don't require a separate theory for confinement at all. It's just kinematically confined. And then recently, and all this is available in that book which he gave to Professor P.R. Whittle. My article contains all the references. Recently, Ashmeet Singh and Carroll, they have taken up this in modeling position and momentum in finite dimensional Hilbert spaces via generalized Clifford algebra. And similarly, they have used this idea of generalized Clifford algebra and position momentum being represented through that in quantum field theory and so on. Of course, then after this, my work in generalized Clifford algebras, etc., ended in around 1983, and after that, I branched off to quantum theory of charged particle beam optics, particularly with my student Samin Ahmed Khan, who is now in Oman, and also with the Professor Anabir Chakrabarti of Department of Theoretical Physics. I went on to do some work on quantum algebras and applications. So I will stop here. Just I want to finish with one, because I didn't write it there. About AB is equal to omega BA, Professor Ramakrishnan has said in one of his papers, the structure is too fundamental to be unnoticed, too consistent to be ignored, and much too pretty to be without consequence. That is dead. Okay.
Thank you so much for your beautiful talk, and concluding with this statement of my father. He had a way with words. He could always express himself so beautifully, and I just have one comment before I call upon questions. So one of the things, I was a student at that time in Vivekananda College, so he called me and said, the beauty of AB equal to omega BA, where omega is the root of nth root of unity, is that A plus B to the power of n is A to the power of n plus B to the power of n. Okay, so if you have that omega commutation relation, that's what you get. Very interestingly, years later, now that I'm working in the theory of partitions, one of the fundamental objects that we work with is called the Q binomial coefficient. So it's a generalization of the ordinary binomial coefficient. When you let Q tend to 1, you get the ordinary binomial coefficient. But the Q binomial coefficient has the interpretation that it's the generating function for partitions where you put a bound on the number of parts and you put a bound on the size of the parts. Okay, so it's a very interesting problem to go from that combinatorial interpretation to the standard combinatorial interpretation of n choose k. It's not easy. But what I wanted to say is, if AB is equal to QBA, right, as a Q generalization of the ordinary commutation, then you find that if you expand A plus B to the power of n, the coefficients are not the ordinary binomial coefficients, but the Q binomial coefficients.
Yeah.
And then if you put that Q to be the root of unity, you get your A to the power of n plus B to the power of n. So I sort of remembered all this thing that my father told me when I was a student in Vivekananda College, but I got this thing later through theory of partition. So it's very nostalgic for many things that you have said. Thank you very much once again for our talk. Are there any questions from the audience? Yes?
Yeah.
When you look at those purely positive energy solutions of the Iraqi equation,
Yeah.
You said it will not couple to electromagnetic field. There are no solutions.
Yeah.
What about other interaction? Does it not couple to others?
I don't know.
Because they are non-abelian. So this is an abelian.
Maybe. I don't know.
If it doesn't couple to any of them, then it will, those positive energy fermions may be candidates for dark matter.
Yeah, that's what my conjecture is, that maybe they are.
It's possible, yeah.
Yes, then the negative energy thing will be the antiparticles, and those two, those two can combine to give dark energy, dark photons.
The matter?
Huh?
What stops it from coupling to other matter? Why it doesn't couple to electromagnetic? Some principle is violated?
No, the problem is that, see, you require a single function to be satisfy 4 different differential equations. So those 4 differential operators have to commute with each other. So only in the free particle case they commute with each other, leading to the condition that E square is equal to m square plus p square. That condition is satisfied. If you put in the electromagnetic field, they don't they are not consistent at all. This.
There is no current conservation.
Some synergy principle,
No, there is no current conservation. That's why Dirac himself let it down. Secondly, also, I don't know whether energy momentum tensor can be done. So if you are able to couple to that, it has to. Yeah. So I don't know, Dirac himself was not satisfied with that. But yeah, there is not minor comment. This equation maybe for omega be. In fact, I have got it in some of the situations what we call nonlinear sigma model, totally nonlinear sigma models. And the possibility of having non-abelian statistics seem to be related to that. That's all. I just had. Probably at that time I did discuss this particular equation with you.
Okay.
With Shankar I didn't discuss.
Thank you for anything more. Oh. Yeah. Oh.
Do you have a copy of this?
Okay. Thank you.
Permit me to make one comment because it's related to what he said. He got this letter from Dirac, and Dirac said, I don't think this has any use in physics or application to physics. Sometimes even the great people could be wrong. One of my last lectures to my graduate analytic number theory class before coming here was on an identity of Ramanujan, which the great number theorist Ingham had used to prove that there are no zeros of the Riemann-Zeta function on the one line. But if you go to Ramanujan's paper, he says, in this paper I'm going to prove about half a dozen identities. They're all very beautiful, so I feel it's worth recording, but I don't think any of these identities have any use. This is what Ramanujan said. But Ingham used one of those identities beautifully with proving that the Riemann-Zeta function has no zeros on the one line, which is, of course, equivalent to the prime number theorem. So sometimes these great people can be wrong. Okay.